Why face is not shown? Face is not shown. Scale to window.
Good.
Stuck with cutter selection. Learn how to choose the right CNC tool. Stuck with cutter selection. Learn how to choose the right CNC tool.
Good evening, everybody. So, sorry for the slight delay in the start. Today, our topic, it's one of the most important practical topics in the CNC machining, yet one of the most confusing areas for beginners and even many experienced operators. The topic is cutter selection. Many people know how to operate a CNC machine. Many know how to load programs. Many know offsets and the setting methods. But when a fresh component comes to the machine, the confusion begins. Which cutter should I use? Should I use the flat end mill or the bull nose, or should I use the 8 mm or the 12 mm? Should I use the 2 flute or the 4 flute? Which is better for aluminum? Which is better for EMS? Which is better for steels? Why did the tool break? Why the finish is poor? These are all real workshop questions. Today, I'll simplify cutter selection in a very practical and easy to understand method. We are not going into unnecessary theory. We are focusing on the real shop floor logic. After this session, when you see a job drawing, you should be able to think more clearly and select tools more confidently. So, welcoming you all again, let us begin our webinar for the day. So, why cutter selection matters? So what happens? Many people, they underestimate the cutter selection. They think that any cutter can machine any job if the machine is strong enough. But In the practical machining, cutter selection affects almost everything. First, the wrong cutter choice can break the tools. For example, using a very small diameter tool for heavy roughing can lead to sudden failure. Second thing, the wrong cutter can create poor surface finish. You may complete the job, but the customer rejects it because of maybe the marks, the lines, the chatter, or the roughness. Third, wrong cutter increases the cycle time. If a bigger suitable tool could remove material in 5 minutes, the smaller may take 15 or 30 minutes, thereby making production loss every day. Fourth, it increases the cost. More tool used, it's equal to more tool wear, more machining time, more electricity, and more operation stress. Finally, a wrong cutter selection affects confidence. The operator becomes nervous, the programmer becomes confused, and the supervisor gets pressure. That is why smart programmers first think about the cutter choice before pressing the cycle start. Now, in many workshops, these problems happen regularly. An operator receives a new component drawing, or the programmer receives the component drawing. Then the first doubt comes, which cutters should I use? Sometimes the tool is selected just by guesswork, or by habit, or by availability. That is why we'll see which is tool available with us. We'll just use it. Then during machining, another program starts. What's the problem? The tool breaks suddenly, or cutting sound becomes rough, spindle load becomes high, or finish is not acceptable, or operation takes too much time. Then what happens? The machine has to be stopped, cutter has to be changed, feed has to be modified, and then again we are trying. This trial and error method wastes time. It is normal for beginners to face this. There is nothing wrong in learning, but our goal is today is to reduce the confusion. We want to move from guessing to logical decision making. A good programmer is not the one who struggles the most. A good programmer is the one who selects wisely before cutting. Now, let's see what we are going to cover today. First, we will understand the common types of CNC cutters used in milling operations. Second, we will understand where each cutter is used because knowing the name is not enough, we must know the application also. Third, we will discuss the flute selection. What is 2 flute, what is 3 flute, what is 4 flute, what is 5 flute, why it matters. Then we will learn the diameter section. So we should use a smaller tool or larger tool. Many people make mistakes here. Fifth, we will discuss how tool choice changes based on the operation. Pocketing, facing, slotting, finishing, roughing, curve profiles, and more. By the end of the webinar, you should not only know the cutter names, you should know how to think like a practical programmer. Now, before we study the cutter types, let us understand the basic anatomy of a cutter. So you can see the top part is mentioned here as the shank. So the shank is the upper cylindrical portion held inside the tool holder or the collet. Second are the flutes. Those are the spiral grooves. Spiral grooves that help create cutting edges and also remove the chips. Next is the cutting edge, which is towards the corner. This is where the actual metal cutting happens. Fourth is the geometry. Some cutters have flat tips, some rounded, some radius corners, and some chamfers. This tip shape decides the kind of feature it can machine. Next is the diameter. Diameter affects strength, reach, cutting load, and material removal rate. Larger tools are generally stronger but may not enter small areas. Smaller tools reach tighter spaces but are weaker. Finally, the coating. Many carbide tools have coatings to improve wear resistance and heat handling. So, before choosing a cutter, understand that it is not just one piece of metal, it's an engineered to j tool with geometry designed for a purpose. Once you understand the cutter anatomy, selection becomes easy. Next. Now we'll go to the HSSs. Before choosing the cutter shape, we should know the cutter material. Two common materials are the HSS and the carbide. HSS means high speed steel. It is older, it is cheaper, and it is still useful in many manual machines or also in the lower speed works. It is tougher than the carbide in some impact conditions, but it cannot handle high heat and high speed efficiency. Carbide, on the other hand, is much harder and more wear resistant. That is why carbide tools are common in modern CNC machining. They can run at higher cutting speeds, maintain edge longer, and improve the productivity. However, carbide is also more brittle. If setup is poor or the tool crashes, it may chip faster than the HSS. So, when should you use what? For modern VMC and production CNC work, carbide is usually preferred. For light duty work, low budget, or older machines, HSS may still be useful. Today, in most CNC shops, carbide dominates because time is money. Next, you may notice that many CNC shops strongly prefer carbide cutters. Why? First, First, carbide can run at higher spindle speeds, and proper feed means faster machining. Second, carbide often lasts longer when used correctly. This reduces tool change frequency. Third, carbide usually gives cleaner cutting action and can improve finish quality. Fourth, it increases productivity. If one tool removes more material faster and lasts longer, production efficiency improves. But remember something important, carbide is not magic. Wrong holder, too much overhang, poor clamping, vibration, or incorrect feed can still break the carbide tools. So, carbide gives performance, but only when the setup is sensible. Think of carbide like a race car. Powerful, but what is needed? A good driver is needed. Now, many people see tool color and think the color itself is the main feature. You can see different colors, maybe copper color, brass color, plain without any color. So actually, many colors, where it comes from? These are coatings. These are thin engineered layers added to improve the performance. For example, if we see the tin coating, it often appears gold color. TIN or N may appear dark gray, black, or violet depending on the manufacturer. What do coatings do? They help resist the wear, they help handle the heat, they reduce friction in some cases, and they can increase the tool life. This is especially useful in steel and higher temperature machining. But remember, coating does not fix wrong usage. If feeds are wrong or setup vibrates badly, coated tools can also fail. So coating, we can say that coating is an advantage, not a miracle. When selecting tools, think of coating as one helpful factor among many. Now, next comes the Flutes. What are flutes? So flutes are the spiral grooves on the cutter body. These grooves create cutting edges and also provide space for the chips to escape. Flute count matters greatly. More flutes usually means more cutting edges and softer core. Fewer flutes usually means larger chip space. So aluminium, for example, uses lower flute counts because chips must evacuate well. Steel often uses higher flute counts because chips are smaller and stronger cutting edges help. Flute count also affects the feed strategy, finish, and rigidity. So when someone says two flute or four flute, they are not just counting the grooves, they are discussing the cutter behavior. Now, two flute cutters. Let us begin with the two flute cutter. A two flute cutter has two cutting edges and large flute valleys. This means that chips can escape easily. That is why two flute cutters are very popular for softer materials. See, softer materials like aluminum can create larger chips and may stick if the chip evacuation is poor. The larger flute space helps reduce that problem. The two flute cutters are also common for slotting because they can clear chips between inside the narrow cuts. However, compared with the higher flute tools, they may have fewer cutting edges engaged at once. So, for some finishing or steel jobs, another flute count may be preferred. The two flute is simple, it's effective, and often the first choice. Maximum chip clearance, deep slotting, softer sticky aluminum grades, lower power machines, safer beginner choice. These are the main features of this two flute cutters. Now, now let's come to three flute cutters. What is three flute cutters? This is most popular in the modern CNC machining, especially for aluminum or other materials. Why? Because it gives a smart balance. Compared to a two flute cutter, it has one extra cutting edge. That means it can often run higher feed rates and smoother cutting. At the same time, it still keeps good chip clearance space, which is important in aluminum machining. So many machinists consider three flute cutters the middle path between chip evacuation and productivity. They are commonly used in pocket milling and side milling, adaptive toolpaths, and production jobs. Can it replace two flute always? No. If deep slotting with chip packing risk exists, two flutes may still be better. But for many CNC VMC aluminum jobs, three flute is the excellent modern choice. Next comes the four flute cutter. This is one of the most common cutters used in a CNC workshop. Why is it popular? Because it gives more cutting edges and generally a stronger tool core. This can be useful in steel machining and many general purpose applications. A four flute cutter are often used for side milling, contouring, finishing, and semi finishing. Since there are more cutting edges, feed performance and finish can be good and when the conditions are correct. However, the chip space becomes smaller compared to the two flute or the three flute. So, in soft materials producing large chips, especially full slotting, the chip evacuation may be more challenging. That is why tool choice depends on the material and operation. For steel jobs, many machinists trust four flutes tools heavily. Now we have the higher flutes. What are the higher flutes? Such as higher flutes matlab like 5 flutes or 6 flutes. These are common in advanced machining environments. Why? Why we have to use more flutes? Because more flutes can mean more cutting edges engaged, smoother finish, good productivity in side milling strategies. They are often used in hardened materials, finishing passes, and high speed machining with lighter radial cuts. However, there is a trade off. More flutes means less chip space. So these tools are not ideal for jobs generating heavy bulky chips in tight spaces. That is why these cutters are often paired with modern tool paths, lighter stepovers, and controlled strategies. Like it's just a specialist tool. We have to consider a specialist tool rather than beginner general purpose tools. Now, one of the most common mistakes in machining is poor diameter selection. Many beginners choose very small tools for everything, but diameter matters greatly. A bigger diameter tool is usually stronger and more stable. It can often remove faster material and resist deflection better. That means better productivity. But a larger tool cannot enter small corners or narrow pockets. Now, small diameter tools are useful when details are tight, radii are small, or access is limited. But smaller tools are weaker and easier to deflect or break if overloaded. So, what is the golden rule? That is, the golden rule is first use the biggest tool that safely fits the feature, and then after the bigger tool has done its work, use the smaller tools. This one rule can improve the machining dramatically. Never use tiny tools unless geometry requires them. Now, we discuss a silent killer in machining, which is known as the overhang. Overhang means how much tool length extends outside the holder. Many people focus only on diameter and forget the tool length. Even a strong cutter becomes weak if it sticks out too far. Long overhaul can cause vibration, chatter noise, poor finish, dimensional inaccuracy, and tool breakage. The machine spindle may be powerful, but the tool behaves like a flexible stick. Here, always the rule is keep the tool as short as possible while still reaching the feature. For example, you have a 100 long cutter and you have to machine a depth of around 60 only. Keep it plus 5 keep only 65 overhang, not more. Use only enough length, not extra length. If deep cavity is required, reduce aggression and choose a strategy carefully. Sometimes changing the holder or tool length solve more problem than changing feeds and speeds. In many shops, it is also called as square and mill. If you walk into a CNC tool room and open a drawer, chances are you will find many flattened mills in different diameters. Why is it so common? Because it's extremely useful. This one cutter can perform many operations. It can machine pockets, sidewalls, steps, slots. It can remove stocks. It can finish walls. That's why it's often the first cutter chosen when a new component arrives. Now think practically. If someone gives you a rectangular block and says make a pocket with a flat bottom, most machinists will immediately think of a flattened mill. If someone says reduce the side profile, again flattened mill. If someone can give excellent productivity and accuracy. If used badly, it can chatter, wear quickly, or break. So never underestimate the humble flat end. Now, where will we use it? Let's go deeper. Where should we use the flat end? First, pocket milling. This is one of the strongest applications. Whenever you need a cavity or recessed area with a flat floor, flat end mill is the natural choice. Next is the slot milling. Slots, channels, keyways, grooves, narrow cuts are often done using the flat end mills, especially the centered cutting types. Third, sidewall cutting. If a profile must be machined on the outside or inside wall, flat end mill performs well. Fourth, step machining. Many mechanical parts have multiple heights, levels, or shoulders. This cutter handles those easily. Fifth, roughing and finishing. Depending on the cutter quality, and strategy, the same tool family can be used for roughing or finishing. Now let's discuss the caution. The sharp corner edges of the flattened mills take stress. During heavy cuts, vibration, poor holder clamping, or aggressive plunging, these corners may chip off. And once the corner chips, finish quality can reduce. That is why many shops shift to bullnose cutters for demanding jobs. But still, For everyday machining, flat-end mills remains one of the strongest choices. And if you understand this tool deeply, you can solve many machining tasks confidently. Next is the ball nose cutter. So this is here we are moving from a flat geometry to the curved geometry. This is a ball nose cutter. Immediately when you look at the tooltip, you'll notice that the bottom is rounded like a half ball. This rounded geometry changes everything. This cutter is not mainly for flat pocket floors. It is for shapes, contours, or flowing surfaces. Where do we see such surfaces? We see it almost everywhere, like mold cavities, die surfaces, automatic styling parts, aerospace shapes, artistic contours, impellers, turbine blades, any component where the surface are not simple straight walls and flat floors. And when CAM software generates the 3D tool paths, ball nose cutters are often used for finishing because the rounded tip can smoothly travel across the changing slopes. Now imagine trying to machine a sculptured curved surface using a flattened mill. You may leave steps, marks, or awkward transitions. Bullnose helps create a smoother version. That is why mold and die industries this cutter is highly respected. It may look simple, but it unlocks advanced geometry. Next, where is ball nose used? Ball nose is used in multiple places. First, in the 3D surface finishing. This is the most famous use. When the tool moves in many fine passes across a curved path, the ball nose cutters help produce smoother surface planes. Second, the mold cavities. The injection molds and the forming dies often contain complex internal surfaces. Third is the radial profile. If the internal shapes require blended curves, ball nose can be useful there also. Fourth, sculpted or decorative components. Fifth, semi-finishing before the final polishing. Now, let us discuss where people misuse this cutter. Some beginners use ball nose for every job because it looks advanced. This is a mistake. If you need a fast, flat bottom pocket, flat end mill may be more efficient. If you need a strong roughing, another tool may be better. Every tool has its purpose. Ball nose is not universal, it is specialized brilliance. Use it where geometry demands curvature. Next is the bull nose. The bull nose, or also known as the corner radius end mill. This cutter combines two useful ideas. It's mostly flat bottom like a flat end mill, but instead of a sharp fragile corners, it has a small radius at the corners. Why does this radius matter so much? Because sharp corners are weak stress points. During heavy cuts or vibrations, corners can chip fast. By adding radius, tool strength improves, tool life often improves, surface transition improves, confidence improves. This is why many experienced people love bullnose cutters. They are because they are practical, they are durable, they are productive. Now, where they are used? They are used for pocketing, semi-finishing, production milling, floor wall blend areas, general machining where sharp internal corners is not required. So many shops prefer bullnose for repeat production because tools last better than the sharp corner tools. It's like a flat end mill is sharp and capable. The bullnose is sharp, capable, and tougher. Whenever drawing allows corner radius, bullnose becomes a very intelligent choice. Now, where to use it? Pocket milling. When a pocket does not require perfectly sharp inside floor corners, bullnose is an excellent option. Why? Because the radius corners of the tool are stronger than the sharp square corners. That means better durability and lower chance of corner chipping. Second, semi-finishing operations. Many shops use bullnose cutters before final finishing because they create smoother transitions. Third is the production jobs. If a bullnose tool lasts longer than a flattened mill in the same job, it can save cost and downtime. So, many drawings do not actually need the sharp internal corners, but people still choose square tools by habit. That habit can shorten the tool life unnecessarily. If drawing permits radius, bullnose may be smarter industrial choice. This is why experienced machinists often smile when they see bullnose tools. They know it can quietly solve the problems. Now we move to a powerful production tool, the face mill. This cutter is usually larger in diameter than the end mills and commonly uses replaceable inserts. Its main purpose is simple and important to machine large flat surfaces quickly. Suppose a raw block has a rough saw cut the top surface. You need a clean, accurate top face. Instead of using a small end mill and taking many passes, a face mill can cover wide area rapidly. That saves time, that improves productivity, that creates professional flat surface. These face mills are common in VMC machines, especially for preparing stock before the further machining. They are often one of the first tools used in a job setup. Raw material comes in rough, face mill comes in, makes it civilized. Also, because inserts are replaceable, many face mills are economical in production environment. So think of this as a tool like a road roller or something like that make a flat surfaces. Where do we use it face mill? So mainly we use it for top surface facing. It's the most common use. When raw material top face is rough or uneven, face milling quickly creates a flat plate surface. Second, stock preparation. Many machinists first face the top, then flip part and face the opposite side to establish reference thickness. Then large plates and blocks. Whenever surface area is wide, face mills save major machine time. Fourth, flatness improvement. Large tools with proper setup can help achieve consistent flat surfaces. Now, where should we not depend on face mills? We should not use it for small narrow pockets, tight internal features, deep cavities, detailed profiles, etc. These jobs belong more to end mills and smaller cutters. So always remember, face mill is for open surfaces and end mill is for the detailed surfaces. Next is a roughing end mill. This is a tool built for hard work. So what's happening? This tool often has a serrated or wavy cutting edges. Some people even call it corn cob style due to the appearance. Why are there these teeth-like edges? Because they break chips into smaller pieces and reduce cutting load behavior in many operations. Its main purpose is not beautiful finish. Its main purpose is to remove material aggressively. Suppose we have excess stock and need to remove large volume before final finishing. Instead of trusting a finishing cutter, roughing end mill can do the dirty work first. Then finishing tool comes later for accuracy and surface quality. This two-stage strategy is common and smart. One tool for bulk removal, another tool for beauty. That is efficient machine. Now, roughing end mill, where we will use? We use it for heavy stock removal. We use it for large cavities. Then the tougher materials where controlled roughing strategy is required, and we use it for the pre-finishing stage. This means that roughing tool removes most stock, leaving small finishing allowances. Then another tool gives final dimension and finish. Now, another important caution. Do not expect showroom finish from a roughing cutter. Its job is speed and bulk removal. It is a demolition team, not the interior designer. Use it smartly, then follow with finishing tools. This roughing and finishing mindset is one of the biggest steps from beginner thinking to professional programmer. Next is a U drill. This tool is also called as a insert drill or indexable drill. Unlike normal twist drills, U drills use replaceable inserts at the cutting tip. Why is that useful? When inserts wear out, many times you replace the insert instead of replacing the whole tool body. This can reduce the cost in production environment. Secondly, U drills are designed for faster drilling of large diameter holes. Third, they are common in CNC machining centers where repeated hole making is required. If a job contains many holes of the same size, your drill can become productivity champion. Now, does it replace all drills? No. Small holes and certain precise jobs may still use conventional drills, but for production hole making, especially medium and large diameters, U drills are extremely valuable. And when students learn the U drill, they step into modern CNC thinking. Next is a twist drill. The twist drill is the classic drill. It's the most recognized cutting tools in the world, whether it is a manual drilling machine, lathe, or CNC machine. Twist drills are everywhere. They are used to create holes in many diameters and materials. They are available in HSS, cobalt, carbide, coated versus, etc. Why are they so common? Because they have simple design, easily available, huge size range, and it can be used reliably. In CNC machining, twist drills are often used for pilot holes, smaller holes, and general purpose drilling. Even though it looks basic, drill selection still matters. Wrong speed, poor coolant, weak clamping, or dull drill can create oversized holes, heat, and breakage. So, never underestimate drilling. Hole making is one of the most frequent operations in machine. Next is a chamfer tool. It is a small tool that creates big professional difference. After roughing, the finishing, the drilling, and profiling, many components still have the sharp edges. These sharp edges may look unfinished. They may cut operator hands. They may create burr problems during the assembly. That is where chamfer tools becomes important. A chamfer tool creates an angled edge, usually 45 degrees in many job, though other degrees also exist. Where do we use it? Outside corners, pocket top edges, mouth of the drill holes, and around the profiles. This will improve safety, appearance, and sometimes assembly ease. Many beginners focus only on major machining and ignore final edge quality. But customers often notice edge quality immediately. So chamfering is not a decoration, it's a professional finishing discipline. When you see an each component with clear broken edges, often a chamfer tool quietly did the finishing touch. Next, let us move to the precision hole finish with a reamer. Suppose you drill a hole. The hole may be acceptable for many normal jobs, but sometimes a drawing demands tighter tolerances, smoother finish, or better fit for shafts and pins. That is where the reamer is used. Usually, a slightly undersized hole is drilled first, then the reamer passes through it and removes a small amount of material. Its purpose is not heavy cutting, its purpose is accuracy. It improves the diameter consistency, it improves the roundness, it improves the surface finish. This is common for dowel pin holes, bearing fits, locating holes, or precision assembly parts. So drilling makes the hole, reaming perfects the hole. So when accuracy is important, more important than the speed, the reamer becomes valuable. The whole, now let's discuss how internal threads are created in CNC components. Many parts need bolts, screws, and fastening points. That means threaded holes are essential. Two major methods are tapping and thread milling. Tapping, the tap cuts the thread directly inside the pre-drilled hole. This is common, fast, widely used for standard threads like M6, M8, M10. Second is the thread milling. A special cutter moves in a circular interpolation path to generate threads. Why use thread milling? Because it offers flexibility. Different sizes may be handled depending on the setup. In some applications, it may reduce risk compared to the broken taps. Especially larger threads or difficult metal can benefit depending process. For most common jobs, tapping is practical and fast. For advanced CNC environments, thread milling is powerful option. Indexable end mill. This cutter uses replaceable inserts instead of full solid carbide body. That means when cutting edge wear out, inserts can be often replaced while the tool body remains in service. Why is this valuable? In precision machining, cost control matters. For large diameter tools or repeated job, replacing inserts may be more economical than replacing complete solid tools. Indexable end mills are commonly used for roughing, profiling, shoulder milling, and general material removal. They are strong, practical, and popular in industrial environments. Now remember, they may not always replace small precision solid carbide tools, but for medium to heavy machine jobs, they are heavily efficient. This is a classic example of modern production thinking, modular tooling for the productivity. Next is the shell mill. It's a large insert milling cutter mounted on an arbor or holder, used for facing and shoulder milling and for high productivity tool. It's best for flat surfaces and heavy milling. This is an important industrial cutter used in many CNC centers. Shell mills are generally larger cutters with replaceable inserts mounted on a cutter body. They are commonly mounted on an arbor or dedicated holder. Why shell mill is important? Because they are productive, they can machine wider surface quickly, they can remove material effectively, they are excellent for facing operations where a flat surface must be cleaned or brought to size. They are also used in shoulder milling depending on the cutter design. Now, many people confuse shell mill with face mill. Simple understanding. Face milling is an operation, shell milling is a type of cutter often used to perform that operation. This means that shell mills are tool bodies used to efficient surface finishing. Another benefit is instant replacement. When cutting edges wear, the insert may be changed instead of replacing the entire body. That makes the shell mills economical in many production shops. Whenever you use large plates, blocks, or heavy machinery setups, shell mills are the common heroes. Next is the helical shell mill. This is still part of the shell mill family, but with a smarter insert arrangement. Instead of insert placed in a simple straight pattern, they are in helical or staggered layout. Why is that useful? When the cutter enters the material, not all insert hits at once. Cutting engagement can become more progressive and smoother. This may reduce the shock load. It may improve sound and the cutting field. It may help productivity depending on the machine and application. These cutters are often seen in modern production machining where a faster stock removal is desired. They also look impressive, and for good reason, a lot of engineering goes into the cutter geometry. This tool says that cutter design is not about sharp edges, it's also about how forces enter the material. So this thing, the best benefit of helical is that it can take out the flat surfaces and also it can do the side milling also. Next is a long reach end mill. These tools are designed for places where normal cutters cannot physically reach. Examples include deep pockets, mold cavities, tall walls, and recessed features. Without long reach tools, some areas cannot be machined. But there's a trade off. Longer tools are less rigid. They can bend slightly under load. They can shatter. They can break if punished too aggressively. That is why experienced machinists always choose the shortest possible tool that is still reaches the feature. Long reach tools solve access problems, but they may require gentle machining and strategy. This is a perfect example that geometry access and rigidity must be balanced. Next is center drill. It's a small but very useful tool, the center drill. When starting holes directly with normal drills, drills can sometimes wander slightly. This can affect the hole position accuracy. Center drills creates a precise starting point. They help guide the next drill. They are commonly used before drilling important holes. They are also used in lathe work for center holes between the centers. Through small size, center drills helps improve confidence in drilling accuracy. Many quality jobs begin with small, accurate preparation steps like this. Next is a diamond or PCD tool. PCD means polycrystalline diamond. These are premium tools often used for aluminum and non-ferrous machining. Why are they respected? Because they can provide the excellent surface finish. They can offer long tool life in repetitive production. They are common in automotive industries and high volume manufacturing. They are not casual low cost tools, they are strategic productivity tools. With the factory machines thousands of aluminum components, tools like this finish matters greatly. This is where the PCD tooling shines. This also teaches us something important. As industries demand more speed and edge consistency, tool technology keeps evolving. Next. So, let us simplify tool selection into quick practical thoughts. So, if a job has a pocket with a flat floor, think of flat end mill. If the job has curved or 3D surfaces, think ball nose cutter. If you need stronger corners and better durability, think bull nose. If a large flat top surface must be machined quickly, then shell mill or face mill. If a hole is required, think drill or U drill, depending on size and production need. If the hole needs accuracy, think reamer or boring. And if internal threads are required, think tap or thread mills. This is not only the rule book, but it is a strong starting point. So, many machining problems are not actually machine problems. They are tool selection mistakes. First mistake, using a small cutter for every operation. Small tools are useful but weak. Second, excessive overhead. Even a small cutter becomes unstable if too long. Third, wrong fluid count. Aluminum and steel may need different strategies. Then, ignore the material type. Fifth, using ball nose for the fast flat bottom pocketing. Sixth, trying one tool for roughing and finishing when the two-stage machining should be smarter. And these mistakes, if avoided, can improve the results faster than buying expensive tools. Now, let's clear a most common confusing confusions. That is flat end mill. What is flat end mill? Flat end mill is a general purpose flat floor cutter, excellent for pockets, slots, and walls. Ball nose is for curved geometry, molds, and flooring surfaces. Ball nose sit between bull nose sits between them in some way. It has a flat capability with radius corners for extra strength. If sharp corner geometry is needed, flat tool may be necessary. If curved geometry is needed, ball nose is ideal. If durability and corner strength matters, ball nose can be an excellent choice. Choosing among these three tools correctly can solve many daily machining problems. Now, every time a new job comes, pause before choosing the tool. What you have to do? Check the material, check the feature geometry, check the diameter that can fix it, check the reach needed, and check whether roughing or finishing is required. Check machine rigidity. And here remember the golden rule. Use the biggest suitable tool that safely fits the feature. This offer gives better rigidity, speed, and confidence. Now, we are going to discuss about two special purpose cutters. First is the T-slot cutters. It is used to machine T-shaped slots. What do we see T-slots? So T-slots will be there in machine tables, fixture plates, special clamping arrangements. So many VMC tables themselves use T-slot systems for clamping the workpiece. To machine a T-slot, usually a straight slot is first made, then the T-slot cutter machines the undercut profile. Second is a dovetail cutter. This cutter is used to machine dovetail grooves and locking the profiles. Where we can see this? We can see is in the sliding guideways, adjustable slides, fixtures, tooling systems. The angled shape helps create self-locating and retained geometry. These are not everyday pocketing tools, but they are extremely useful in specific engineering jobs. Their presence reminds us that the machining tools are designed around the geometry needs. Whenever geometry changes, the tool design also changes. So, that brings us to the end of today's webinar. Today we covered many of the most commonly used and important CNC cutting tools used in the machining industries. We discussed where they are used, how to choose from, and the logic behind smart cutter selection. Of course, the tooling world is vast. There are many more cutters, special purpose tools, custom tools, and advanced tool systems used regularly in different industries. But my goal today was to give a strong practical foundation so that next time you see a job, drawing, or machining operation, you can think more confidently about the tool selection. So, thank you all for attending today's webinar. I truly appreciate your valuable time and participation. At Operal Education, we focus on industry-oriented practical training for students, freshers, and working professionals. Admissions are currently open for a 45-day CNC operator cum programmer course. This program is designed to build practical machine knowledge and job ready skills. And I'm also happy to share that we'll be soon starting our online SolidWorks training program, which will be useful for students, diploma holders, engineers, and design learners. And if you're interested in joining in any of the programs, please contact us through the phone numbers and email shown on the screen. We'll be happy to guide you. Once again, thank you for your support. Please like, share, and subscribe. And that's the end of the class. If any doubt, you can please enter in the chat box. I'll be replying it slowly. So that's all for today. Thank you. Have a nice day. See you on the next Saturday webinar.